screen. Okay, so let me step. Something is problematic. Okay, yeah, so this. So desktop, I think I'm having some difficulties. Okay, so let's see. So yeah, so let's look at the following theorem. Okay, so let. Yeah, I think the desktop there's some. Okay, I think there's some. Left. Oh, okay. Yeah, I'm having some difficulty writing it. So my laptop is not working, so that BKB. What's it? Yeah, I cannot write it. So yeah, I'm going to show some parts of the book and highlight what I wanted to say. So I think unfortunately I cannot write today. Hopefully in the next lecture I'll be able to bring the laptop or make some arrangements. Okay, let me open the PDF file. Okay, so why this is not coming? I don't understand. Okay, so this is not coming. So basically, so what we're going to say is that if you have an endomorphism, of an elliptic curve.
Sir, can you zoom it? I can't read.
Okay. So let me say, I think because the desktop, I think the applications are not coming that properly. In my laptop, things are all smooth. Laptop is not working for. Let me just try it in a different way. Let me open it from the.
So which writing pad are you using?
Welcome.
So maybe installing the driver would work, make it work fine.
So actually, the things are all is. I mean, mine is the Apple desktop.
Yeah.
In my Apple M1, I mean, mobile, no, on the laptop things were fine, but this is my desktop, and somehow things are not okay. I don't know what's okay. What's happening? Let me just try with XP. What is the other one? Well, both are same. One is the desktop one, but in the laptop things are all working fine. So I was hoping that will be fine, but let me just see good notes once again. Yeah, so okay, so yeah, in that case, yeah, let me try to find out. Okay, so some other way to do it. Okay, so, hmm. All right. So yeah, by the next lecture I'll fix. Let me just see if there's something else which I can. Oh, okay. Yeah, I think that's fine. So let me then present something which so this may work. Okay, so let me just see if you can view this. So screen. Can you see the screen, all of you?
Yeah.
Fine. So yeah, so I'll show you some from. I mean, yes, a little bit discontinuity, but this is also good. So I'm going to show you this notes today, and next time I'll make arrangements to write and give this. So the model way was supposed to come later on, but I think we can today we'll just look at the elliptic curves over Q. So if you want to look at the structure of elliptic curves over Q, then there's a famous result of Mordell-Weil, which tells you that the elliptic curve over Q is a finally generated abelian group. So in a way, every element, like, so there are points P1, P2, Pn, such that every point can be written as a linear combination of P1, P2, Pn.
Can you zoom a bit?
Okay, you want to zoom a bit more? Okay, let's see. Then maybe I'll make it fully. Okay. So, So is it okay? Is it better?
Yes, sir.
Okay.
Yeah.
Yeah. Okay. So yeah. So this is the well-known model, result which says that the points on the elliptic curve is actually a finitely generated abelian group, and here, yeah, I mean the is generated by n points, so where n is called the rank of so n is called the rank of this rank of the elliptic curve, and the as we know that the points on elliptic curve is actually they form a group. This is usually called the model-well group, and yes, and there's this weak model-well theorem shows that for any m, if you look at this m, so remember that EQ is a set. I can think of it as a set or of course a group. So MEQ means m times. So for every point here, you take m times that point. So this set MEQ means the set of all points of the form MP such that P is in EQ. So there is a subgroup of the EQ, and the quotient group EQ over M. EQ is a finite group for all m bigger than or equal to 2.
Sir, what was EQ?
So EQ means the set of all points on the elliptic curve. You remember that if you have an k, like now we are having q, but given any field k, ek. So okay. Yeah. Okay. So given any field, so E bracket k, so that means the set of all points on the elliptic curve. So and we know that that forms a group. And when k is q, we call the group as the model-well group. And okay, so yeah, so these are model and under-well. And for any m bigger than 2, so bigger than or equal to 2 MEQ. So given a set, given a group G, and G is a additive group, then you can define 2Z. So 2Z means 2 times the elements of G, right? So for every point you write 2 times the elements of G. So that is actually going to be a subgroup of the original group. So original group is EQ. So then you have the subgroup MEQ, the quotient group. So it's finite. So that is the weak model-well theorem. And okay, so the weak model is in general EQ need not be finite, but the quotient group EQ over MEQ is a finite group. So that's the weak model-well theorem. Okay. So yeah, so later on we'll prove model-well theorem in the course, but so right now I'm showing something which is I'm not going to prove it the model-well today, but later on I'll prove it. So I wanted to go in a sequence from the book of Washington, but there are some issues today, so I'm showing it here. So what it follows, the model-well theorem tells you that every element can be written in terms of finite number. So you have P1, P2, Pn such that every element is a linear combination of those points. So then from there it follows that the set of the group is isomorphic to a torsion part and a free part. So by the theorem of finitely generated abelian groups, you have a torsion part plus a free part. Okay, so the first set, what is this torsion point? So torsion points is nothing but points of finite order. So that means the set of all points for which there is some whose order is n for some fixed n, and the other part is the free part. So it's an important problem in this elliptic curves to see whether for a fixed n do we have an elliptic curve of the range. So here the order Re. So Re is the range. So in fact, EQ is EQ torsion plus Z power Re, where Re is the range. So range could be 0, 1, or anything. So the question is, can you construct an elliptic curve of a given range? So that's an open, I mean, sort of very difficult problem in elliptic curves. A lot of work is going on in that direction. Sometimes I'll show you about those things. And here I want to just, so Re here is called the rank of the elliptic curve. And so we want to, so here we want to say, tell you is that if you take the set of all points which are of infinite order along with the point at infinity, this is not a subgroup if the torsion group is non-trivial. So if the torsion group is you remember that this, so the point at infinity is a part of the torsion group because one times n equal to 1 works. So torsion group is a subgroup, it's a non-empty subgroup, but it's a trivial group. Then set of all points of infinite order intersection union with this is a subgroup, otherwise it's not a subgroup. So anyway, so let's look at some examples. Yeah.
What did you say now? When is it subgroup and when is it not?
So what I was saying is that if you just take set of all points of infinite order along with the point at infinity, it may not be it's not a subgroup. Like unless the torsion group is non-trivial. I mean, if the torsion group is trivial, then this is going to be the whole group. So so in that case, it's a subgroup. Otherwise, it's, I mean, so so as you can see, you have the torsion part and non-torsion part. The torsion part is trivial, then the so all the points except the point at infinity is of infinite order. So just giving an example here for so if T is a torsion point, and then a P is of infinite order, then this P and T, P plus T belong to F. I mean, it's a point of infinite order. But T, which is so P is in the set, and P plus T is in the set, but T is not in the set. Okay, so let's try to look at some examples of these elliptic curves with the model world group. So if you have this elliptic curve y square equal to x cube plus 6, it has no rational points other than a point at infinity. So in fact, so over Q, this has no points other than a point of infinity, and so hence there's no torsion points other than a point of infinity and no point of infinite order. So rank is 0, and set of points of set of points on the elliptic curve is just the point at infinity. Of course, we need to actually really do prove it, but it's not that difficult here because things are smooth. Here we know these things explicitly. And y square equal to x cube plus 1 has 6 rational points. And when x is 2, y is 3 anyway, you can see it's a solution. I mean,
So there at example 1, there is no solution over Q?
Yeah.
Okay.
And example 2, you know that 3 square is equal to 2 cube plus 1. So 2, 3 is a solution. In fact, its order is 6. And yeah, so in fact, the points on elliptic curve is isomorphic to Z over 6Z here. So the rank is 0 here too, yes. So the points on elliptic curves are given, I mean, so Z over 6Z is an element of element of order 6. So it doesn't have a free part. I think somehow this is very uncomfortable here. Okay. Now let's look at another. I mean, so of course, unfortunately, I cannot write down and show it explicitly, but
So in
yeah.
last example, how do you know like there will be only 6 rational points? Like
No. So here, this is actually computed. So yeah. So the later on actually will. So what we know is that we have a final this. Yeah. So here in this case, actually, okay. So we need to really say that if you start with any point, but by looking at it, it's all going to be final. I mean the torsion point. So we need to actually work it out. So later on, actually, when I have to write, so I'm going to work when we completely go to elliptic curves over Q. Yeah, so that time we'll work it out completely. So here I'm just, I mean, so one way to see is that you start with a point like 2, 3. So then, yes, I think okay. Maybe I can show you like here. This one is completely done. So there is some. Yeah, when you rely on something and then that doesn't work, it's a bit trouble. Oh my goodness. Okay. Just jump side. Why is okay? So yeah, I think I have to make it is okay. Just a sec. Let me just try it. Yeah, so this is a small. Okay. Yeah, so the thing is that yeah, so I'll just go to the example 2.34. Yeah, so okay, control. Can you see it? Okay, is it a bit bigger? Can you see this? I think this is better. Yeah. Yeah, so this is the elliptical y square equal to x cube plus 1. Yeah, so then what happened? Yeah, so for the point 2, 3, you have this point 2p, then yeah, okay, so then 6p becomes a point at infinity, but it doesn't tell you that the okay, so there are no point at infinity, but this requires a little bit of work. So in fact, we'll see some algorithms to compute the rank of an elliptic curve. So that will tell you that this the rank of. So later on we'll see about the rank of an elliptic curve. So that tells that this has rank 0. and they will tell you that only the points are torsion points, and they are given by this. And y square equal to x cube minus 2 doesn't have any rational torsion points other than 0. Okay, so yeah, so what we'll do is that you know that 5 square equal to 3 cube minus 2. So can all of you see this? Are you all able to see this, guys?
Yes, sir.
Yeah, so this one, maybe this is easy to score. So this, if you look at this curve, y square equal to x cube minus 2, it doesn't, so you know that 5 square equal to 3 cube minus 2. So 3, 5 is a rational point, but it doesn't have any torsion points other than the point at infinity. So that, and you will see, in fact, there's this Navier-Stokes theorem which tells you what are torsion points. So 3, 5 is a rational point. So since there are no other rational, another torsion point, so it must be a point of infinite order. And so hence this, there are infinitely many points on this curve. So it turns out that the rank is 1 and is generated by 3, 5. So so this is isomorphic to Z. So I have said it easily, but we actually were going to really dirty our hands, and so we'll really see how the points and how torsion points look like, or the rank looks like. That's one. And this one, this another elliptic curve. Okay, so in this example, the first one doesn't have any rational points except the point of origin. Second one doesn't have any point of infinite order. Third one has point of infinite order, but no rational, no torsion points. The fourth one has both torsion points and non-trivial torsion points and point of infinite order. So here, the points on elliptic curves is given by this. So there are four points of finite order, and the torsion subgroup is generated by this a point of order 4, and yeah, so there are 3 linearly independent elements. So free part is generated by 3 points of finite, this order. So right now you can just trust this, but later on we'll really see how we can actually how we can compute these points of infinite order, etc. Okay. So as I mentioned before, the rank is a measurement of arithmetic complexity and is not known if we can yeah, so if we can have a elliptic curve of very large rank. So right now the largest known rank is 28. So we don't know an elliptic curve of rank 29 over Q, 29 or higher. So it's, yeah, this is one of open problems where we saw that for arbitrary, you can have elliptic curves of arbitrarily large rank, but so far, this is not proven. So this is, so that's another point of research. Where a lot of work is going on. Okay, so now, yeah, let's come to the torsion subgroup. So Mordell-Weil theorem tells you that elliptic curve has a torsion part and free part. So rank is given by the free part, and torsion parts are points of finite order. So now let's see. We'll come to the result of measure, but before that, let's see this example. So if you have this elliptic curve given by, for a fixed n, if you look at elliptic curve y square equal to x cube minus n square x, so it has 3 obvious rational points 0, 0, minus n0 and n0. And yes, by using the some like doubling of the points, you can see that these points are of order 2. And it turns out that yeah, so these are all points of order 2, and the torsion subgroup of this elliptic curve is isomorphic to z over 2z, direction z over 2z. So now Mordell-Weil theorem tells you that torsion subgroup is always finite. There are only finitely many torsion points. So then, what kind of abelian groups can appear as the torsion subgroup and elliptic curve? In this case, there's a well-known theorem of Mazur. It was originally Oak's conjecture, which tells you that torsion point is always an is isomorphic to exactly one of the groups, z over nz with n less than 10 or n equal to 12. So that means you cannot have a torsion point of more than 12 elements. So torsion subgroup of more than 12 elements. Either this happens or z over 2z plus or is isomorphic to z over 2z plus z over 2mz, or n lies between 1 and 4. Yeah, so this is a famous measure. After this is over Q, then there has been like a lot of work on UX replace Q by a number field or a finite extension of Q, and there's also quite a bit of work is known, and a lot of work. People are looking at this, trying to compute the torsion points on elliptic curves over cubic fields, over any number of fields. So, and it turns out that you can find elliptic curves with torsion points from like for each of these possibilities, you can find elliptic curves of the torsion point. Okay. Yeah. So So for example, so there's a table here. Yeah. So here torsion is trivial, and x cube plus z torsion is z over 2z, and x square plus xy is torsion is z over 10z, and y square equal to x cube minus 4x, the torsion this form. So so over Q we completely know the torsion points, how to compute the torsion points and what are the torsion points.
So can you go to last page?
Last page, okay. This one. This is a measure.
Okay.
So basically z over when n is 1, just this is a trivial one element group, or or n equal to 3 up to 10, but n equal to 11 is not there, n equal to 12. Okay, so sorry that today today I'm not able to write anything. I was to go from elliptic curves over modulo n and other things, but unfortunately that's not working. So, so I'll come to Navier-Lewin. So this is one of the so we're going to actually prove this Navier-Lewin in the so today I'm giving just a glimpse, but we'll prove all these things. Okay, so this is if you for a parameter b with Husserl rational, you look at the elliptic curve y square plus 1 minus bxy minus by is x cube minus bx square. Here the discriminant is non-zero. Then torsion group. So the torsion group is actually 0, 5. So in fact, this kind of examples people created so to find infinitely many elliptic curves whose torsion is fixed group, like one of these groups above. So we'll in the course of lectures, so we'll see about this also. I mean, we'll see clearly. Okay, so Mazur's theorem says that any point of finite order should have it should have order less than or equal to 12. So if it is something more than 12 or 11, then it should be point of infinite order. So yeah, so this is one way to check whether yeah, so that one of your questions were how do you know that rank is 1? So this can be used. So only it can tell you that okay, so rank is non-zero, but it cannot. I mean, Mazur's theorem just helps to check whether there's a point of infinite order, but doesn't tell you whether rank is going to be 2, 3, 1, whatever. So yeah, so there's a well-known theorem of Navier-Lewis, which we will be actually giving a proof in this course. It tells you explicitly, given an elliptic curve with Weierstrass equation in this form, x cubed plus ax plus b, then how the torsion point looks like. So torsion points means it's the point xy of finite order, and if the torsion point is its coordinates are integer, that means p is xy, then yeah, so like if p is xy, then x and y has to be integer. So basically, torsion points are all integer points. And if it's a piece of order bigger than or equal to 3, then 4a cubed plus 27b squared is divisible by the y coordinate, square of the y coordinate. So yeah, for example, if I take x cubed plus x plus 1, so a equal to 1, b equal to 1. Yeah, so then a point of order bigger than 3 should be this. So y coordinate should be the y coordinate should divide 4 plus 27 is 31. So you don't have any point of order. Yeah, so Navier-Lewis theorem is very powerful theorem. So if you take a equal to b equal to 1, then 4 plus 27 is 31. So and yp square should divide 31 means yp has to be 1. So any point of order bigger than or equal to 3 should have y coordinate 1. So then you solve for 1 is x cubed plus x plus b. Then you can try to solve for x. And if p is of order 2, then y coordinate has to be 0. And y0 means x coordinate x cubed plus. So the solutions, the roots of this equation x cubed plus x plus b gives points of order 2. So for example, so it's giving an example when a is 0, b is minus 2, then 4a cubed plus 27b square is 27 into 4. It should be divided by yp square. So that means yp should divide 3 into 2, so 6. So yp should divide, this means yp has to be plus minus 1, plus minus 2, plus minus 3, plus minus 6. Now, in this case, you can see that, xp, like you can have points of order. So xp cube is 3, yeah. So when yp is plus minus 1, if you put then xp cube is 6, a is 0. So x cube is y square plus 2. So you can explicitly write down. So the torsion point is trivial. So from here one can actually write down the torsion. It is a non-trivial. It is a trivial torsion subgroup. Is that okay? So like once Navier-Lewis theorem is known, then you can explicitly write down all the torsion points of a elliptic curve, of an elliptic curve. So another example is the following. If you take a prime P and define the EP to be elliptical given by y square equal to x cube plus p square. So x cube plus p square has no rational root, so it doesn't contain points of order 2. See, it's a p of order 2, then x should satisfy this, so there's no point of order 2. Then if the torsion subgroup, then 4a cube plus 27b square should be divisible by p square. So b is p square. So 27b square means 27 into p power 4. So y which divides y square dividing 27p power 4 r plus minus 1 plus minus p. Yeah, so plus minus 1 plus minus p square 3p then 3 plus minus 3p square and plus minus 3. And one can see that none of this, I mean, when y is 0, then x is 0, then plus minus p is a solution. And in fact, it turns out that these are the only points. You see, p square plus minus 1 cannot be a square. So we can see that none of the other points give a torsion point. Okay. So the torsion subgroup is actually isomorphic to Z over 3Z. Is that okay? So anyway, I mean, of course, I've not proved the Nagier-Lewis theorem, but this is a very powerful theorem. So we'll prove it. It's quite interesting. And once you know it, then you know the torsion points quite clearly. So one way to find whether it is I mean, if a rank give a bounded rank is to find a non-torsion point of so find more. I mean, if you can find two so the two non-torsion points, then then you expect the rank has to be at least 2. So that's how people try to come up with the rank. Is that okay? So any questions here? All right, so that's about the torsion. So now I want to say something about the elliptic curves over finite fields. Let me just see. So okay, so consider the finite field Z over Pz, and you consider elliptic curve over Fp. So for example, y square is congruent to x cube plus 1 modifies an elliptic curve defined over F5. And one can check that it's a cubic equation. So later on, so one property of this elliptic curve is that it has to be smooth curve. So if you look at this y square equal to x cube plus 1 mod 3, this is not elliptic curve because it's not smooth. In fact, p is 2, 0 is a singular point. So its derivative at 2, 0, the partial derivatives at 2, 0, this are all 0. So we'll see what given a point, I mean, given an equation, is it going to be really an elliptic curve? So there the notion of discriminants will come into picture. So I'll define what's a discriminant in a moment. So let's take elliptic curve given by the Weierstrass equation. Then you can reduce this, our a and b are integers. If we reduce a and b modulo p, then an equation given by this cubic curve over finite field Fp. So E can be an elliptical smooth curve over Q, but the reduction mode P may be singular over Fp. So I'm not defined what's a singular curve. In fact, I had yeah, I was to write down about the singular curves, but unfortunately, today I'm not write anything. I'm not able to write anything. So we'll explicitly mention what is this singular. So like y square equal to x cube plus 1 is smooth over f and f over q and f5, but it has a singularity at mod 3 over f3, right? So if the reduction is smooth, then it's an elliptic curve over P. So to understand whether any given elliptic curve, whether it's smooth or not, so we come to the elliptic discriminant. So here I want to also tell you something. Sometimes the reduction of a model of an elliptic curve is not smooth, but it can be smooth for some other models. So yeah, for example, y square equal x cube plus 16525 is not smooth over f5 because 0, 0, you can see that it's a singular point. But model means is isomorphic. So you recall, so with the invertible change of variables, we get a new model which is given by y square equal x cube plus, or this is which is smooth. So these two curves are isomorphic, but but then this is something called is not minimal. So we're going to define what's a minimal model. So we'll come to that. So by model means you have an isomorphism. Like you can have a change of variable and you get it, but given an elliptic curve, by change of variable, it may not. It may not be smooth if you take modulo some prime. So let's formally define what is the discriminant and what's the minimal discriminant. Given an elliptic curve, y square equal to x cube plus x plus b in Weierstrass form, then the discriminant delta denoted by delta e is given by the formula minus 16 times 4a cube plus 27b square. So unfortunately, because I'm not able to show this, so later on we're going to really talk about discriminants, how it's coming, and for a more general Weierstrass form, how does discriminant look like? I'm going to show you to you, but today, yeah, I'm just giving you more of a glimpse here. So given an elliptic curve, let S be the set of elliptic curves which are isomorphic to E over Q. So we have already seen, endomorphism is isomorphic. If the endomorphism is isomorphic, then we call them isomorphism. It's isomorphic to E. And such that discriminant of this E bar is an integer. So you take this elliptic curve E prime whose discriminant is an integer and which is isomorphic to E. Then the minimal discriminant is the integer which is given by the minimum of the absolute value of all the discriminants in the set S. So in other words, the minimal discriminant is the smallest integral discriminant of an elliptic curve that is isomorphic to E over Q. And if E dash is a model of E with a minimal discriminant, we say E dash is a minimal model for E. So here we have an example. So so basically, given any elliptic curve whose Weierstrass form is given by x cube plus x plus b, you have a discriminant. So if the discriminant is 0, then it's not an elliptic curve. And when you say whether this elliptic curve modulo p, whether this is smooth or not, so modulo p, if this is 0, then it's not going to be smooth. So it's not going to be elliptic curve modulo that p. Then we have this minimal discriminant. So equation x cube plus 5 power 6 as a discriminant. which you can just use this formula a0 b is 5 power 6. So we have minus 2 power 4, 3 square 5, 12. And x cube plus 1 is discriminant, minus 2 power 4, 3 square. So yeah, so later on, yeah, so in fact, I was to tell you when two elliptic curves are going to be isomorphic. So yes, yeah, so we'll see about this. So since E and E prime are isomorphic, so this delta I cannot be the minimal discriminant. So and hence it's not a minimal model. So it turns out that minimal model is given by this this elliptic curve, and minimal discriminant is given by minus 432. So today, yeah, so I'm just showing you the different definitions and just showing an example, not explicitly finding. So we're going to show how to find this minimal model and how to show that two curves are isomorphic. Okay, so okay, so types of singularity. So let E tilde of an elliptic curve over Q K with an Weierstrass equation given by this Weierstrass equation. General Weierstrass equation. Suppose E tilde is a singular point. Yeah, so singular point, then you can write by Taylor expansion of over two variable fxy minus fx naught y naught is this lambda. So you can expand it. You can write y minus y naught minus alpha x minus x naught times y minus y naught minus beta x minus x naught minus x minus x naught cube. So yeah, you can write in this form. So here this lambda i's yeah, so lambda i's are in K. So in fact, you can write it as lambda 1 x minus x naught square plus lambda 2 x minus x naught times y minus. So yeah, you sort of look at Taylor's expansion, then lambda q plus this, and you write in terms of alpha and beta, where alpha and beta are in algebraic closure. Yeah, so then we define this, what's a cusp and what is a knot. So a point, singular point is called knot if alpha is not equal to beta. So you factor out the above one in this form, then if alpha is not equal to beta is called cusp, a knot. Then in that case you have two tangent lines, say P, okay, and alpha is beta, then we say P is a cusp, and there's a unique tangent line at P. In fact, this is used to also draw the graph of the elliptic curve. Okay, so yeah, so then there's this notion of good reduction of elliptic curves, which is quite important. Let you have an elliptic curve given by minimal model and prime P bigger than or equal to P, and E tilde with the reduction modulo P. Okay. Then you have an elliptic curve modulo P, suppose it has a reduction. So that means it's a smooth modulo P. Then we say smooth reduction if E tilde is a smooth elliptic curve over FP. And if E tilde is singular at a point P, then we say EQ has a bad reduction at P, and we distinguish these two cases, like depending on cusp or not. So if E tilde is a cusp, then we say yes, unstable reduction or additive reduction. And it has a knot. Remember, knot means alpha is not equal to beta here. Then it has semi-stable reduction, so it or multiplicative reduction. And if the slopes of the tangent lines here are in FP, then the reduction is said to be split multiplicative. Otherwise, I mean, non-split. So, I mean, so here depending on alpha, so that basically alpha and beta, they are in FP. Then we call it split multiplicative, otherwise non-split. So the first thing is that if there's a good reduction means we can define it modulo FP. So for example, y square equal to x cube plus 35x plus 5. It is a good reduction at p equal to 7. The modulo 7, this x cube plus 5, it is a non-singular curve. One can check. But if you see modulo 5 is going to be just y square equal to x cube, in that case, it's not going to be a good reduction. Bad reduction. So it is a bad reduction at p, because in that case, you can write the equation as y minus 0 square minus, I mean, so x cube equal to y square, which you can write it as y minus, so y minus x square, y square minus x cube. So so basically y minus 0 minus 0. So image slope is 0. Now, these are also some other examples. So when y square equal to x cube minus x square plus 35, that's bad multiplicative reduction at 5 and 7. So because modulo of 5 is going to be x square minus x square. So which you can write it as so y minus 2x plus y minus, so minus x cubed. So remember that minus x square is minus 1 means 4. So so y square minus 4x square is called x cubed, which you can write in this. So in this case, because this both are same, that's why it's split, and over 7 is not split. So so these are very important terms. So reduction and the reduction is split, non-split. So so these are very important terms. So it's one should definitely know. So, and another example is basically elliptic curve given by model y square plus y is x cube minus x square minus 10x minus 20. Here minimal discriminant is minus 11.5. So it's a prime of bad reduction. So those things are coming. So basically, once you know the discriminant, you can talk about the prime of bad reduction and split, etc. So here we're not giving any proof, but I'm just showing you some propositions. So in the next lecture, in the subsequent lectures, we're going to actually prove many of these results. So let's start with the field K. Oh, sorry. Okay. Because full reduction. Yes, this proposition. So let K be a field and Ek is a cubic curve given by y equal to x cube, where fx is a monocubic polynomial. Suppose you have the roots alpha, beta, gamma in fx, then put d to be the discriminant. So basically, given a cubic, you have this discriminant of cubic, and this discriminant is called the discriminant of the elliptic curve. Then E is a non-singular if and only discriminant is non-zero. So the way we find the discriminant of an elliptic curve is that you have the roots alpha, beta, gamma of the cubic. Suppose if you have y square equal to x cube plus x plus b, then the roots of that equation, x cube plus ax plus b, where alpha, beta, gamma, they will give the discriminant d. And if the discriminant is non-zero, then it's called non-singular. So it's non-singular if in fact it's if and only. So the alpha minus beta square, alpha minus gamma square, beta minus gamma square, gamma minus alpha square is called the discriminant of the polynomial, which is in fact the discriminant of the elliptic curve. In fact, I mean, yeah, so it's a multiple in the sense that discriminant of the elliptic curve is given by 16 times t. So we have a sort of, depending on the minimal model, we can say whether it has a good reduction or bad reduction at p. So let you elliptic curve be, I mean, let's take an elliptic curve with coefficients in z and p be a prime. If it has a bad reduction, then p has to divide the discriminant. So if p doesn't divide discriminant, then it has good reduction. And in fact, if E is given by the minimal model, then P divides discriminant if and only if E has bad reduction at P. So here elliptic curve y square equal to x cube plus 35x plus 5. Discriminant is minus 2 power 4, 5 square 71, 87, 97. So if at all it has a bad reduction, it will have the primes 2, 5, 71, 97. Yeah, so then so E1 has a prime, a good reduction at 7, but bad reduction at 2, 5, 71, 97. And you can talk about this whether unstable reduction, etc. I mean, by looking at this modulo this primes. So thing is that good. I mean, once you know the discriminant, then only we need to worry about the primes dividing discriminant. Once the prime doesn't divide the discriminant, we know it has good reduction. So things are nicer there. This is hello, Indigo. Yeah, I'll call you back after 1 or a minute. Okay, so yeah, you have this elliptic curve. Yeah, so these are like given an elliptic curve with integer coefficients over Q, then you can talk about a good reduction. So just you have to remember that once you know the discriminant, the good reduction means where prime doesn't divide the discriminant, bad reduction means it divides the discriminant. Yeah, okay, so then this is about the over Q. Now over a finite field, suppose you have an elliptic curve defined over a finite field, which where Q is a P power R. Then where we can ask how many points are there. So let NQ denote the number of points on the finite of the elliptic curve over FQ. Okay. So then definitely this is going to be finite. Remember that FQ is finite. So and coordinate XY can come from finite, means number of points over elliptic curve over FQ has to be anyway finite. So the well-known term Hasse gives a bound for these points on the finite elliptic curve over the finite field. In fact, if E tilde is elliptic curve defined over FQ, then the number of points lies between Q plus 1 minus 2 root Q and Q plus 1 minus plus 2 root Q. So in fact, this understanding this n cube minus q plus 1, so this is one of the important aspects in the modular, I mean, like in the theory of elliptic curves and modular forms. Okay. So an example of an elliptic curve over Q is y. I mean, like, okay. So where we have, so we have this consider elliptic curve y square equal to x cube plus 3. This minimal discriminant, which which you can assume now is that 2 power 4 into 3 power 5. So primes of bad reductions are only 2 and 5, and for primes bigger than or equal to 5 is all going to be smooth. When over F5, this has 6 points. Yeah, so when y is 0, x cube, so then 3. So 3 cube plus 3 is, is 5. So now n5 is 6. So now q plus 1 minus 2 root q is 1.5 point something, and q plus 1 plus root q 10.4. So number 6 lies between 1.5 and 10.4. So there can be huge gaps depending on if q is small or large. Okay. So this is the famous term of Hasse. In fact, connection of these points on the elliptic curve, number of points on elliptic curve with the points on cube are, so it has connection to one of this $1 million problem called Burst and Swinton-Dyer conjecture, which is related to the growth of NP with the rank of the elliptic curve. Okay, so today I'm sort of giving you more advanced talk in the sense that, so these are the points. So basically you can start, the point of what I'm trying to say is that you can start with a simple elliptic or cube, but then you can have a lot of connections with many other entities, and which are still, some of them are known, some of them are not known. So this, in fact, these are notions which were developed also during the proof of, while trying to prove Fermat's last theorem. So let's start with let's look at an elliptic, another example. So points of order dividing M. So let E over Q is elliptic curve, P is a prime and M is an integer not resolved by P. Suppose elliptic curve over Q has good rejection at P, then rejection mode P. So EQM means so these are the set of points which divides, whose order divides M. So yeah, so basically the point at infinity is here because its order is 1, so it's here. So EQM means the order can be M if or any divisor of M. So from here there's a map, reduction map, which is an injective homomorphism abelian group. So once this is injective, so once you know the points here, you can try to find the points of some given order. So in other words, number of elements of the points of order dividing M will divide the number of elements of this elliptic curve over FP. Yeah, so these are the notions which also try to have you. So if you so if you want to find so you have asked me one of the questions. So how to get the rank? So this also connected. Okay. So if you have a okay, so it tells you that for any given M, if you want to count the number of points of given M, it has to come from this. So if you take different primes, so you take a fixed prime P which has a good reduction, then number of points of order dividing M has to divide that points on the elliptic on EFP. Now you take another prime, then it has to divide. So if you take the GCD of them, then somehow you can make it smaller and smaller. So what I was telling is that this is quite useful in calculating torsion subgroup and elliptic curve. So let's look at an example. So y square equal to x cube plus 3. So we've already seen that number of points on the from this finite field F5. Yeah, so F5 is actually 6, and over F7 is 13. And EQ has a bad reduction only at 2 and 3. So yeah, so this one we have seen before. So if you take a prime which is different from 5 and 7, then we can see that number of points of order dividing Q is actually trivial. So I mean, yeah. So why is it? Because if you take a prime which is different from 5 and 7, it has to divide 6 and it has to divide 13. So it should divide 6, GCD of 6 and 13, which is 1. So it has to be only trivial. Okay. So is it okay? So any questions here? So the previous theorem, which we of course we didn't prove, this is very powerful in the sense that we can try to use this to calculate a torsion subgroup. So what you can see is that for any prime order, if you want to find the element of some order, yeah, so element of yeah, so for any m, if you find element of order dividing m, we can find easily, but once you know the points on the number of points on FP with two given FP, like n5 and 7 we know, then we can know that for any prime different from Q and 7, it's all going to trivial. So now when Q is 5, we know that it has to divide n7, which is 13. So if the points of order dividing P is non-trivial, then P will divide P will divide this cardinality, in fact. So so basically, actually, I mean, we'll also see in the course of lectures that this number of points on elliptic curve, so the subgroup of points of order less than or dividing P, it is going to be subgroup Z over PZ into Z over PZ. Sorry. So, but it just talks about torsion subgroup. Now, okay, so if you look at this y square equal to x cube plus 3, it doesn't have any point on the, I mean, so we know that 1, so 1, 2 is a point on the curve, and it doesn't have a point of finite order. So this must be point of infinite order. So it has infinitely many rational points given by plus minus p, plus minus 2p, plus minus 3p. In fact, it turns out the rank is 1, and 1, 2 is a generator of model well subgroup. Yeah, so so basically Navier-Stokes theorem tells you where to find the torsion points, but we can we can use this modern this notions to see which one we can make it better. Yeah, so what I was saying is the following. Okay, sorry. Okay, so sometimes this proposition is more useful and more effective than using Navier-Stokes theorem to compute the torsion subgroup. Oh, well, so now, okay, so let's try to look at the rank and free part of the elliptic curve. So maybe I'll take a short break here and yeah, so maybe short break for 5 minutes. So you can ask me if you have any questions, then we'll talk about rank and free part of EQ. So today I'm just giving a glimpse, and yeah, next week on Thursday we don't have a lecture, but I'm going to give you some exercises from what we have done, and then yeah, so later on we're going to prove all these results. So yeah, so we'll take a short break for 5 minutes. So if you have any questions, do let me know. Huh? Okay, fine. So let's continue. Mm. Okay, so let's see how much. Yeah, I think okay. So what I'll do is I'll just give these topics and then just introduce to some of these concepts, and then next time we're going to anyway prove many of these things. Well, mm, so Mordell-Weil theorem tells you that elliptic curve has the torsion part and free part, the rank of the elliptic curve. So the free part gives the rank of the elliptic curve. So yeah, now the question is that you asked, so how to find the generators of the free part of the these things. Yeah, so the thing is that unfortunately we don't have any method, like to find the rank, but we use, but by using the notion of knife height theory, we try to give a upper bound for the rank, and from the upper bound, we try to find out whether we can completely keep a rank explicitly. So, okay, so here this is a very interesting aspect. So if the coefficients, coordinates of generators, if the coefficients of the Weierstrass equation is small, then we expect that coordinates of the generators should be also small. And but then this is not the case. Actually, Bremner and Kessels found an example of a curve y square x cubed plus 877, which is rank equal to 1, and x coordinate of the generator is quite big. So that's why then so this is towards how to find the rank, and Lang, Search Lang, so he conjectured that for all. So, the conjecture that given epsilon, so for epsilon positive, you can find a constant such that the points of the generator, so should be bounded by some constant, bounded times the power of a square root of discriminant, where the height of the, so the so-called canonical height functions. We have not defined what's the height. So the canonical height of this point should be bounded by this constant times the square root of the modulus of discriminant. So this is a conjecture of Lang. So so what it says is that if the minimal discriminant is large, then the height of the generator should be also, it should grow exponentially, and coordinates will grow exponentially. So let's try to define the heights here. So height is coming from the, it's a generalization of this maximum and minimum of the numerator and denominator of a rational number. So for a rational number, m by n in the form with GCD mn equal to 1, we define the height to be log of maximum of m and n, and maximum of n. Okay, so maximum of m, modulus of m, and modulus of n. So given a point P on an elliptic curve with x, y, and q, then you can define the height of P to be height of the x coordinate. So yeah, so this is the height now. But what we're interested in the canonical height. So the canonical height is actually given by this. You take the height of this doubling. So 2n p 2 power n p by so 2p. When is n is 1, 2p by 4, then 4p by 16. So you look at this height of 2n power p by 4 power n, you take limit and take 1/2. So 2n dot p is the multiplication of curve by using, so doubling, yeah, so doubling of the point. So that way canonical height is not actually that easy, right? I mean, just you have to do the doubling, then you have to take after that the height of that maximum of yeah. So this upper bound and the numerator and denominator, then you have to take the maximum log of the maximum divided by 4 power n. So here you have this. Okay, so consider this y square equal to and p with the generator, which was quite big. Then some of the values of this height, this by when n equal to 1, 2, 3, 4, etc. is this 47.86, etc. So the yeah, if you from here, if you see the limit is actually, it turns out that the limit is equal to 47.990159 something, which is well below the value of the half of the discriminant. Okay. So we'll also see some computation to, I mean, like we'll use this SAS program to find some of the heights too. So there's a huge, I mean, literature and theory about these heights. So yeah, so following following some properties of this height, I mean, canonical height due to Néron-Tate. So you have an elliptic curve, and if I tilde the ice head with the canonical height on E, then yeah, it satisfies the parallelogram rule. So height of P plus Q plus height of P minus Q is 2 times height of P plus height 2 times height of Q. Yeah, so and another is this in saying, so for any m, integer m, height of MP is m square height of P. Yeah, so in a way, height of this MP is much larger than height of P. Okay, for m not equal to 0 and 1. And if a point for any point P on the elliptic curve, so height is always bigger than or equal to 0, and this also tells you that height becomes 0 if and only if it's a torsion point. So yeah, basically this height can be also used to find the torsion. I mean, like if you know poles of, I mean, so all the points which have canonical height 0, then that's how going to be torsion point. So the proof of these things require quite a bit of things. We aren't going to prove it. Anyway, today we cannot anyway prove anything. So I just want to tell you that there's a lot of work going on. I mean, like a lot of things are going on here. So yeah. Okay, so by using this Néron-Tate height, in fact, there are work to give some rank of an elliptic curve. So if you have an elliptic curve given by Weierstrass equation, y square equal x cube plus x plus b, and if R is the rank, and okay, so denote by nu n to be the number of distinct prime divisors of n. So omega, actually, yeah, we usually use omega of n, but here is the nu of n. Then the rank of an elliptic curve is actually given by the number of prime divisors of a square minus 4b plus number of divisors, those distinct prime divisors of b minus 1. So more general, so yeah, so basically even if you don't know what is the rank, but it gives an upper bound for the rank. So more generally, if E over Q is an elliptic curve with non-trivial torsion, point of 2 torsion. 2 torsion means point of torsion point of order 2, and let A be the number of primes of this additive bed reduction, and M be the number of primes of multiplicative bed reduction. Then rank is also given by M plus 2M minus 1. So the thing is that once you know the discriminant, then yeah, so after that you look at primes where it has bed reduction. Then you try to look at number of primes of additive bed reduction and multiplicative bed reduction. Then rank is also given by M plus 2M minus 1. Okay, so this is a very important theorem in the sense that though we cannot say compute the rank, but it just gives an upper bound. Right. Now, Fermat, okay, so Fermat proved that 1 is not a congruent number. Remember that congruent number means, yeah, so it's an area of triangle with rational sides. Area of a right triangle with rational sides. No, with rational sides, that's right. So, Fermat proved by showing that this equation x power 4 plus y power 4 z square has no rational solutions. So by using this this theorem above here, we can show that y square equal x cubed minus x has only trivial solutions, which are torsion points of order 2. So let's look at this elliptic curve here. This minimal discriminant is 64. So P is the unique point of prime of bed reduction. And of course, we have to check that prime 2 is multiplicative. So you look at this, that alpha beta, you say an alpha, then you look at that this is multiplicative. So multiplicative means M plus 2M minus 1. A is 0, then M is 1. 1 minus 1 is 0. So that means rank has to be less than or equal to 0, means rank is 0. You see, if M is 1, definitely if A is 0, M is 1, then this is less than or equal to 0. But rank cannot be non-negative, so it has to be 0. And E1 has only torsion points. Then we could find all the torsion points. So then that's how then we can find out all the points of this points here. So another example is y square equal to x into x plus 1 x plus 2. So here, so we can try to find the rank. Yeah, so the bound for the rank. So the by writing in the form AB, so you can find that a square minus 4b is 1, and sorry. So you have the Weierstrass equation. So remember that we're looking at the equation y square equal to x cubed plus x square plus b. So when this is in this form, x cubed plus x square plus b x, So in this case, AB is 1, 1, 2, then rank is also less than, rank is 0. And torsion points one can check. So when y square equal to x, x plus 1, x plus 2, rank is 0, and you can find torsion easily. And another example is the elliptic curve is in this form. 2 and these are primes divisors of b and a square minus 4b. Then the rank becomes 3. So then we find 3 primes, 3 points of infinite order, and which are the, so here of course we need to find the generators of the free group, and so and it turns out that we were able to find 3 points, which are, which are sort of, which gives the generators of the free group. So these are the linear independence. Then it comes up, talks about, so we need to talk about what is the linear independence of rational points. So here we are mentioning that the points P1 here, P2 here, and P3, these are infinite order, and subgroup generated by P13 is isomorphic to Z cube. I know that rank is 3 and subgroup generated by is isomorphic to Z cube. So what does this mean? So that means now we are talking about the linear independence of rational points. So how can we show that? So you have these 3 points whose subgroup generated is isomorphic to Z cube. How can we show that? Given 3 points, can I write, whether P3 is a linear combination of P1 and P2. So these are kind of questions we need to ask. So this is related to the linear independence. Okay, so let's look at the definition. It's like the way you know. So you have these 3 points P1, P2, Pn over EQ. So these are called linearly independent over integers if you can find n1 m and m integers such that n1 p1 plus n2 p2 plus nm pm is t. So now where t is a torsion point. So remember that when we talk about linearly independent means sum is 0, but here we're not writing this, so we just take a t. The sum should be a torsion point. Otherwise, if it's not a torsion point, then you cannot find any linear combination whose sums to a torsion point, then we call them linearly independent over Z. Okay. So I want you to understand the difference of linearly dependent over Z of this curves from the other general definition of linear dependent. So over a vector space, usually linearly dependent means it sums to 0, but here, so 0 is replaced by a torsion point. So for example, if you look at the equation y square equal to x cube plus x square minus 25x plus 39, and if you take P1, P2, P3, it turns out that minus 3P1 minus 2P2 plus 6P3 is 0. So these are linearly dependent. And here another example, y square plus y equal to x cube minus x square minus. So later on, actually, we'll just see concrete example. Through this program, we'll explicitly show this example. And okay, so y square plus y. So in this case, if you take P1 to be this point and P2 to be this point, so these are two rational points which are linearly dependent, because you can write minus 3P1 plus 2P2 is this, which is a torsion point of order 5 in this curve. Hmm. Okay, so I think, oh yeah, so now definitely the next question is to ask, uh, can we find a method to prove that some number of points are linearly independent? So to do that, we need to bring in this neuron-tet pairing. So which actually it's, yeah. Yeah, okay, yeah, so we need to bring neuron-tet pairing. So maybe I'll just define it so that we'll stop after this. So neuron-tet pairing is a pairing of an elliptic curve by point. So you have a map, bilinear map from PQ to EQ where given points PQ, you define it to be the height of P plus Q minus height of P minus height of Q. Okay, so and the canonical height. Okay, so yeah, so these are the real numbers. So start with R rational points. You define elliptic height matrix to be our cross R matrix given by this. Yeah, given by this points PQ. So Pi, Pj, where I and J runs between 1 to R. The determinant of this this elliptic height matrix is called the elliptic regulator of the set of points. And if you start with a complete set of generators of the free part, then the determinant is called the elliptic regulator. Okay. So the thing is that, yeah, so you have this some points are rational points. You have this elliptic height matrix, which are given by this bilinear maps, and determinant is called elliptic regulator. Now, if you start with a complete set of generators, then the determinant is called elliptic regulator of the elliptic curve, PQ. Okay, so that's the definition. And yeah, so you can connect with this. So this one, we can say about this torsion point based on this bilinear map. So for all PQ, of course, this is symmetric. One can see easily. And yeah, in fact, this is a non-degenerate symmetric bilinear form, of which also you can see. So PM cube and R is n times PQ plus NPR. And if P is in, yeah, suppose P is a point on the curve such that PQ is 0 for Q, then P is in the torsion, is the torsion point. So in particular, P is a torsion point if and only if the I mean the function this bilinear form is 0 for at PP. So these properties, I mean, these are simple properties which follows from the definition. But what is important is that we have the following corollary, which is quite important. Suppose you start with this R rational points on the elliptic curve, and I see the elliptic height matrix, which we have just defined. Suppose the determinant of the elliptic height matrix is 0, and UB, yeah, so UB is in the kernel of this height matrix. So yeah. Okay, so yeah, remember, yeah, so remember, I just want to recall. Even P1 to PR elliptic height matrix is given by this narrow depth pairing, right? The value is that narrow depth pairing. So if the determinant is 0, and yeah, so you take u in the kernel of this. You see, H is the R cross R matrix. So you look at this linear map given by X, and you take a point u in the kernel. Then this PIs, these are linearly dependent, and this N1 and NK PK K from 1 to R gives a torsion point. And if the determinant is non-zero, then these points are linearly independent. So, and rank has to be at least R. So this neuron pairing, it gives it gives some condition of whether these points are linearly independent or not. So I think my class is more or less over. So I'll just stop by showing you this with this example, and it's a good time to stop now. So for example, if you look at the elliptic curve y square equal to x cube plus 230 at x square plus this, then take PQR in these 3 points. Okay. So whether if you have to find out whether these are independent, you found the elliptic height matrix. I mean, later on I'll introduce you to SES, so we'll compute this. So you compute this neuron pairing values. Determine is very close to 0, but it's not 0. So that means PQR is not independent. So, but then by using this, so you want to find the approximate kernel, kernel, and it turns out that P plus Q minus R is 0. It's a point of order 2. So these are linearly independent. Now, instead, if I take 3 points, and it turns out determinant is 1.00, which is which is non-zero. So in that case, these are linearly independent. So now here, determinant seems very close to 0. Basically, these numbers are not completely exact, right? So that way, when something is very close to 0, we expect that these are, this should be, these are should be not independent. When something is quite away from 0, then these are linearly independent. So I'll stop for now. So I'll meet you next on Tuesday. And before that, I'll try to give you some assignment questions. Okay. So we'll stop for now. So any questions that we can discuss. Okay, all right. So then we'll meet on Tuesday. Okay.